Okay, we're ready to go. So a couple of years ago, I was taking images at OSP, and in one of the images I came across these real small little white dots, and they're called quasars. And besides being able to determine that these are very far away at the edge of the visual universe, a couple of years later I decided, well, what else can you do besides seeing another little white dot that looks like an ordinary star up there? And one of the things is measuring the redshift by taking a spectrum image. So a couple of years ago, I started off with the purpose of being able to measure the redshift of a quasar that's billions of light years away. So this is kind of my journey through that process. And what we're going to see is that those little white dots have much more information than we can see by taking a look at the spectrum. So let's start out with some background information. Light is part of the electromagnetic spectrum. So if we go ahead and take a look down here, we have radio waves like AM, FM radio, we have microwaves up here, infrared, we get to a visible portion here, and then beyond that we have ultraviolet, we move on to X-rays and gamma rays. There's a way that we describe these electromagnetic waves, and that is the distance between each of the either the troughs or the peaks, and we call that the wavelength. And we measure those in meters, or in this case, nanometers, which is very small. Or there's a common thing in spectroscopy is called angstroms, which is historically more common in a lot of the trade and press. The other thing to realize in this electromagnetic spectrum that contains light is that there's energy associated with each one of these waves that wherever we pick. And the energy starts out very low, and as the frequency, and the frequency I mean by how many cycles of this passed at one point in time. So as we move up here, there's many that pass a point in time. Here it's less. So it's related to the wavelength. The wavelength times the frequency equals the speed of light. So the energy increases as we get up here. And that's going to be important because that little piece of information is going to be the key to understanding some of the capabilities that we have in being able to detect what we see. So let's take a look at that spectrum of light. The easiest one Mother Nature provides us is a rainbow. The rainbow, what we see, is caused by the refraction, basically the reflection inside a small water drop by 4 or 5 times, depending upon the primary rainbow or the secondary rainbow. And that disperses the light. And over here, we're going to light wavelength in nanometers. So down here on the very short wavelength, we have ultraviolet, we get into the blue, we move into the cyan, green, yellow, orange, and red, and then we get into, again, the long wavelengths. One thing that's interesting when you get into this is that people see at the edges different amounts. So, for example, typically as you get older, your ability to see out here into where it fades out to nothing decreases, and it gets in, and what you see is less of the spectrum. So that's just an interesting thing that comes with age, and when you start to see what other people can see, and you say, oh, I don't see that. Well, that's because as we grow older, this edge here moves in, and we don't see as much as that violet portion. So, one of the simple steps when you're doing this, what's our low-cost way of doing a spectrum? Well, up here, we're going to take a piece of CD, and down here we have a screwdriver laying on a black piece of felt, and we're going to observe the spectrum of the sun reflecting on this the round shaft of the screwdriver, hits the CD, and we can observe with our eye, or in order to give you that same experience, I take a camera and I take a picture up here where this is. So how do we build such a thing? Well, first you need a piece of CD, and you remove the label. There's some people use shipping tape. I find that compressed air on some CD labels, we just blow it off cleanly. Now, to help things out here tonight, I've cut up some CDs, I've already blown off the labels, so I'm gonna pass this little tray around. Appreciate only one per family, and that way, if you want to duplicate this, you will be able to do, provide your own screwdriver and a black tube to do that. Now, at the end, at the bottom of the tube, just to prevent lots of light coming in and washing out the image, all you do is you cut basically a square, let's say, rectangle in here. And this can be open. In fact, you can do this with this wide open, but in order to take a picture decently, you basically want to reduce the amount of reflected light coming in. This is the top end. And what we have is, in fact, this is a 3-inch mailing tube. And all I do is I wrap some black felt and stuff it in the tube to prevent any reflections off the wall to give good contrast. And then you just cut out a circle disc with a circle in it and black tape, and you tape the CD, and then you put another disc on top of it in order to cut down any reflections on this. Oh, by the way, the equivalent, all the CDs have information tracks. These information tracks effectively result in about a little greater than 600 lines per millimeter transmission grading. And that transmission grading does what effectively a prism does. It takes light and then disperses it out according to its wavelength. So, here we have a picture taken of our, and we got the blue, we got the green, and we got the red. And one thing when you're in astrophotography, you'll learn that something's in focus, everything else is out of focus. So I picked basically this green part here, where these dark lines, and you can focus on it, and you notice that it kind of blurs out here and blurs out here. So the area of interest right now is going to be focused on this part. So we have a continuous spectrum, but the picture I just showed you doesn't really fit that model. It fits basically what we call an absorption spectrum. There are some dark lines in there. In fact, if we go back, you notice that these are slightly bowed. They're slightly bowed because the CD is round, and these lines literally are round. So you will see a slight curve to them. That's normal when you're using a CD. If you had a professional grading, they would be vertical. Okay. So let's go ahead and talk about Kirchhoff's radiation laws. And because this is a fundamental continuous spectrum, that means that we've heated up a solid, like an incandescent light bulb. So it's hot in energy, and it radiates across a continuous spectrum. Or you can have a gas, and you heat it up, it will radiate across the continuous spectrum. But if we ended up with a cool gas, and we can end up with either absorption or emission, depending upon how the light is going through that, and we're going to see that coming up. So, light bulb here, or the surface of a sun or a star, produces a continuous spectrum. That's because energy is bouncing around, and we're going to see all kinds of wavelengths coming off of that. When we come through the sun's protosphere or atmosphere, that is, relatively speaking, a cool gas. And what happens is that all this radiation goes through, hits that cool gas, and some continues on through and to the observer, like this little telescope, and other, basically, wavelengths disappear, and we got basically an absorption spectrum here. So, now we've gone from a little piece of CD to the world of astrophysics. How does this relate? Well, let's start with a hydrogen atom. So we got one proton in the center, and what we effectively have is one electron, and that electron can have different energy levels around them. And the ones that we're going to be most interested in is at energy level 2 to energy level 3. When we have something that jumps from 3 to 2, we end up with red H alpha light. and that's at a wavelength of 6 by 6.3 nanometers. If the electron was already at energy level 4, it jumps down to 2. That's what we call H beta, which is 486486.1 nanometers, and that's this green, blue, green, or cyan, and that's an emission line there. If we go from n equals 5 down to 2, we end with H gamma, and H gamma is 43.4, and I can still see this, and it turns out to be a very nice violet. But now I've got old enough that I don't see this, which goes from N6 down to N2. In other words, at 410 nanometers, I don't see this violet anymore. Now, these are things being emitted. When an electron drops to a lower level, it loses energy. In the process of losing energy, that energy is conserved and emitted as a photon of light. So the net energy stays the same, except when the electron loses energy to go down to this level 2, that photon goes off. Now, if we want to get an electron down here up to this energy level 3, in other words, a 2 to 3, we have to give it energy. And we have to give it energy exactly the amount of this wavelength of light here. So we can move the electron back up here, but that means we're going to absorb a piece of light. So, the key here, the elements have a set of protons in the center, they have neutrons. We change the neutrons, we have different isotopes, and we have basically different ionization with different levels of electrons. So all these three things combine to give us very unique sets of energy levels. And every energy level has a unique pattern in the spectrum of light. So by taking a look at this absorption or emission, we can determine the elements that light has gone through. In other words, the cool gas or the surface of the sun or even the nebula that we'll find out a little later. So here's our wavelength. This is down in the radio waves all the way up to gamma rays. And as this gets very short, in other words, minus the 15th over here, the frequency is inverse because if I take wavelength times the frequency, that equals the speed of light. So as one increases, the other one's got to as one increases like frequency, the wavelength has to decrease. If we take a look at these areas that are white, those are the areas in which the atmosphere is transparent. So we see visible. Now, that's good for us because we get to see the stars in the visible light thing. But in the infrared or ultraviolet, our atmosphere starts to look black and it doesn't allow those energy levels to hit the surface. That's why our infrared astronomy telescopes are perfectly above the atmosphere as high as possible in mountains, like Mauna Kea or in Chile, or we do that in space. So we get above the atmosphere here. But the key thing is that as I move shorter in wavelength or up in frequency, the energy is Planck's constant times the frequency, and that delivers me an amount of energy here. And for example, here with a little marker here, just slightly below the hydrogen alpha radiation, I have 6.6 times 10 to the minus 7 meter. Here's its frequency at 4.5, 10 to the 14th hertz. But more importantly, this is the unique frequency, energy of that wavelength of light. So, going back to our CD, if I take a scale here, and I put a copy of that picture, I can see here's some dark lines here, I get some dark lines here, very faint dark line out of focus. These map, see here, this is the absorption line of H alpha in the sun's atmosphere. The D lines right here, a couple of them, is called the sodium doublet. The E line, which is F, which is not on here, the F line is just about right here. The V, 1, 2, and 4 are magnesium triplets, which is down here. And then we have the F line, which is H beta. So visually observing, the magnesium triplet, the sodium, and the H beta are very obvious in the CD spectroscope. And you use that basically to, just like you look at constellations, use these markers to determine where you are in the spectrum. And then you can know, once you know where those big markers are, then you can start to determine the fine structure, what's down in here. So, to do that, we take the spectrum and we plot it out. So the intensity here is represented by a line. So, see this dark line here? That's a dip. Notice that it doesn't go all the way to 0, it's just a dip, and we see contrast. Here's the dip for the magnesium. By the way, this is H beta here. And notice that here's the emission spectrum of hydrogen. Here's our H beta, here's our H alpha. Over here, I have my sodium, and here's the sodium, basically doublet, and there's the absorption lines of the sodium doublet up here. Magnesium, I have the triplet right here, and that's where I see the triplet up here. So if I take a look at this, I say H beta, here, that's that dip right here. The magnesium, there's the magnesium triplet, there's that kind of wide line there. It's sodium doublet, there's the sodium up here, there's the line here, which happens to be where a cursor is. And then here at this line, we have the H alpha up here in the red. So literally by looking at each of these little lines here, I can start to determine the chemical composition of what I'm looking at. Down here, I have the red line here and a red line here. Those are for the hydrogen lines. I have, let's say, the blue lines are here for the sodium, and then there's the little green box. There's some green lines down here. Here's the magnesium triplet. So these are, again, these are reference markers as to the wavelength of these emission lines. And this is the spectrum of the sun. So let's go back to our CD. And what we do is we plot out the intensity. So we got H beta over here, the sodium over here, the magnesium triplet here. And once you start doing research in this, you find out, wow, look at this. Fe1, that's a iron in the what I call neutral state. We have titanium sitting here. We have lots more iron. And you notice that there's lots of iron sitting here. We have some nickel here. We have some calcium here. So what we have is a variety of different elements that represent by these absorption that are in the protosphere of the sun. So the surface of the sun is this continuous radiation. This radiation is coming through the cooler gas of the photosphere, and when it hits that, these energies are absorbed by those atoms, and the absorption causes the electron to move to a higher energy level in that atom. So this is a zoomed in portion. Here's a zoomed in, this is our H beta, here's our iron, here's iron with titanium, and we have another iron. What this means is that the two lines are so close together that in practical purposes, we can't resolve the differences here. Now, this right here is reinforcing that we have a hydrogen atom that has an electron in n=2 state, and it's absorbing exactly this amount of energy, which is represented by this wavelength or frequency, and it bumps that electron up to n=4, and that's why we don't see that light coming to us, because the atom has absorbed that energy. Notice it didn't absorb it to n=3. If it was n=3, that energy would have been shown as H alpha. And if it was on n=5, that would have been even lower down there. That would be H gamma. So here's a zoomed in portion of the sodium. Notice we even get an indication that there's two separate lines with a little slight rise here. Sodium is much more complex. It's got more electrons, protons, neutrons, and its quantum states are a little more challenging. It still has a primary quantum level n=3, which is the same, but we have a new number up here representing L, which is the orbit momentum calculation in the quantum. So what it means is that the electron jumped from here up to this, and that is 5896 angstroms. Or if it jumped up here in red, we have 5890 angstroms. So literally 6 angstroms different. What's different in this is that the orbital momentum is exactly the same, but the electron is spinning what we'll call plus 1/2 or minus 1/2. And when the plus 1/2 is in the same direction as the orbital momentum, we get slightly higher energy. If the electron is spinning in the reverse direction in which it's orbiting, we get slightly less energy. And this difference in energy accounts for having 2 different lines fairly close together, or what we call a doublet. So down here in the bottom, we have basically the yellow spectrum. It gets real dark here, gets a little lighter here, dark here, and of course, you can see some of the small finer shades here, but this is the star of the show right here, which is the sodium doublet. So, next step, you scrounge around and you realize that all those things you've been buying at used camera stores and things can be made into something useful. And that is, this is an old junk camera body. Doesn't even have a back on it. But the neat thing about it is that you put basically a set of razor blades on where the film rail is, and I have now made a slit. I am holding a 85mm lens. That is where the light comes in, hits the slit, and it starts to diverge. This is a 105mm manual lens, which collimates that and makes that light path from that slit into parallel, and it hits the CD-ROM. The CD-ROM here is on a slight, let's say, angle, and the idea is to reflect that. And the CD-ROM reflected surface will disperse the light, and we need to capture it. We could have captured it with an eyepiece here, or in this case, I've got a DSLR. As you can see, this is real sophisticated. It's called craft work on craft paper. They just cut up and make a dark housing for it, aim it at the sun, and we can take a picture with a higher resolution. So this is approximately about 1,200 lines per millimeter. And you notice that we've done much better on the focusing. Here's our sodium doublet in the yellow here. We have then the iron here, we have the magnesium, we have H-beta. But we can see down here the calcium, the dark lines of the calcium. In fact, the dark calcium lines are much deeper than any of these lines here, but because they're in the violet, it's very difficult for us to see the differences in that. Here's a high resolution spectrum. So these are the long wavelengths, and there's multiple strips. So think of this as a very, very long, maybe a couple 100 feet long picture, cut up into strips, and they're all stacked on top of each other. This is where the H-alpha is. Here's the sodium doublet. Here's the magnesium triplet. Here's the magnesium 1, 2, and 3. Now notice that we're even seeing in this high resolution lines in between them. With this high resolution, that is iron. So that's another, once you determine that you can see all 3 of these, the next challenge is, can you see the iron line separated from here? And that gives you an idea of how much resolution your spectrograph has. Here's the H-beta, and then we get it down in here, the dark lines. Some of them are the calcium lines down here. So, lots of spectrum pictures were taken in the end of the 19th century, early 20th century, and people were starting to classify that. And what the first classification was simple ABC and so forth. And then at Harvard, as they were classifying it, Marie and John Cannon basically discovered that you could reorganize them based on the intensity of the lines. So you notice right here, H-beta, it's not as intense. It gets real intense here in the A and then starts to basically fade out. H-alpha has very similar capabilities, and H-gamma has Meanwhile, magnesium gets more prominent down here, and the sodium also very faint down here, gets more prominent here. And what people have discovered is that these patterns here relate to the temperature of the star. So the star sitting up here is very hot. And as you go from very hot to very cool, we end up with this spectral sequence. And it's reordered. They kept the old terminology. So OBA, fine, girl, or guy, depends on. KISS me is the acronym that's used to memorize the sequence down here. And then, of course, this doesn't have everything in the universe. There's always exceptions, and we'll see some of those exceptions that don't follow in this, but a good class of stars follows. Now, here's the astrophysics behind this. We saw, in order to see H alpha, beta, and gamma delta here, that we jump from n equals 2 to some of the n higher numbers. That means that if the star is so hot, and we never get to the N2, it's always an N3 and higher, that's why these lines get weaker. So there's very little opportunity to ever get down to N2 because it's very hot and everything is basically bumping around and thermal, and as a result we never get down to cool. If we go down here in these cool stars, this is a case where the electron's always at n equals 1. It never gets to N2. In other words, as a bottom level. So in this case, the radiation is totally in the ultraviolet, and we don't see that because fundamentally it's not in the visible n equals 3, 2 to 3 to 4 or 5. And that's true with fundamentally all the rest of the lines. You have basically emissions that are determined on what the transition states are, and if you're too hot, you can't basically have it, or if you're too cool, you can't have it. So fundamentally that brackets as basically the intensity fades in and fades out. So fundamentally the hydrogen series peaks out in the class of stars we call the A stars. Oops, wrong direction. So in summary, O, B, A, fine, girl, kiss me. We're up here at 28K to 50K Kelvin. And notice how the temperature decreases down here as we get cooler. And notice also the color changes from blue to white, yellow, orange, and red. Notice that there's no green stars. So whenever you see an astrophoto with green stars, that's a Photoshop thing. It's not real. This is the color that you're going to see radiated effectively from it. Here we see that it peaks out, and the A are strong for the H lines, and the Balmer series is what the ground state is n equals 2 and higher. That's called the Balmer series. Other features of different chemical elements. So, for example, helium plus lines, and you got strong UV conditioning all the way down here to the star now is cool enough that you get a molecule. A molecule is 2 atoms. So 2 atoms are cool enough. It's cool enough that 2 atoms can join together and we get things like titanium oxide. These are the mass ratios with respect to the sun. The sun, by the way, is a G2. So in here, in a G series is where a sun, and that's where 1 would be. We also get the radius reference to a sun, and we get the luminosity, and we also get an effective age of how long. Notice that our sun, we expect to be around 10 gigalight years, or giga years, is the age of the sun before it goes out. If you had something a little hotter, much less time, 10 million years. If you're nice cool, guess what? You have a ripe old age of 56. And remember, the age of the universe is only about 13 to 14 giga years. So literally, some of these things will be longer than the known universe right now. So you plot that stuff. You get the famous Hertzsprung-Russell diagram. This is called the main sequence. Right here is our sun. Notice we're right. And we reference everything to respect to the sun. So here, over here, we have the luminosity. If it's brighter, oh, if it's dimmer, down here. We also have the temperature. So here's again, the spectrum sequence, O, B, A, fine girl, kiss me, and here's the temperature. So again, things over here are going to be red as far as the stars. We get into orange, we get into yellow, and then we get into the white, and then we get into the blue-white range. And then, once we get the temperature, you can have different sizes of stars in that vertical stripe. So everything here in the yellow goes from very large to our sun to down to the dwarfs down here. So this is a way that you can classify and describe where this star that you're looking at in the HR diagram. So, contrary to what we were told last Saturday night, it was clear. So, unfortunately, the person who delivered the cord of wood dumped it on where I normally put my telescope, so I took a tripod out and took a picture of Orion. So Orion's on the side, the three bright stars here. Here's the M42 Orion Nebula, and over here you see Betelgeuse. And this is a 10-second picture on a tripod, so it's not, you don't see the star trailing. If it was 20 or 30 seconds, these start to turn into a dash. But you start to get a hint that, yeah, some of these are slightly different in color. But here's the experiment you can do. You retake the picture, you do it 1 minute, and you change the focus every 5 seconds. So I'm purposely blurring out the focus of the star. And we can see that these are definitely blue stars. And blue stars are O and B type stars. If we take a look over here, notice the brown or the reddish, and of course Betelgeuse, nice and brown and red. Those are our red stars, and they're K and M stars. So this is an easy way to basically determine the color of the star, and then you look in the star chart and you do the reference, and you'll find that it's all match. The odd one here is the nebula. The nebula has a different color tint to it, and we'll get to that a little later. So, next up, we're going to put a grading filter. This is called the Star Analyzer. It's 100 lines per millimeter grading. And what you can do is you mount it in an adapter for a 55 millimeter lens. Unfortunately, this didn't have a 55, it's 72. So you get a step down range from 72 to 55. You screw it all together. So you take this big glass and you're going to reduce it to a 1 1/4 inch telescope. You're going to take a picture. And the key is that you can put it on a tripod and you just rotate the camera just right. So the stars are now drifting over a 1 minute time interval. And what happens is smears up. So these are the stars, and we call that the zero mode. If the spectrums are generated by that diffraction grating, we are off to the side. So some of them are dimmer back here, like this is dim here, but we definitely see the 3 bright center stars in the belt of Orion. They're very similar. We got this up here, which has also similar. But notice this one down here is somewhat different. In fact, we can see that the blue section of the spectrum is quite a bit shorter. The red end of the spectrum is quite a bit longer compared to here. So with a simple little grading, we can do some astrophysics and say, let's take a look at the chart. So I zoom in, and I have basically, this is a DSLR, so there's a blue, there's a green, and there's the red. So notice, the blue is the smallest of the green, and then red. So this is pumping out more energy in the red portion, and that's our M2, and the AB is a very large supergiant type. Notice over here, the belt of Orion, L11, which is an O 9.7 IB, notice that the blue is the highest, then we get the green, and then we get the red. So literally now, we can use these ratios here to start to determine the temperature and whether or not what the classification of the star is. Pleiades, of course, was above Orion, so why not take a picture of that This is very difficult to see, but there is right here, there's a real faint line here, there's a faint line here, and there's a faint line here. That's H beta, gamma, and delta. So these are the absorption lines of that star and the Pleiades. So now, what happened up here is that there's enough bright stars that overlap these smears. So this spectrum down here and this spectrum here is the best to take a look at and do the analysis on that. That's what you do. You take the star analyzer, 1¼ inch filter, and you mount it into a CCD camera wheel. And there's also a star spectroscope, which is 200 millimeters per lines per millimeter, and that's mounted next to it. This is clear with no filters in it. And these two filters are for photometry. One is a visual filter, and the other one is the blue filter, and basically to do photometry measurements. So this is more or less my science wheel that's mounted in the CCD camera. So I don't take, let's say, RGB, which is pretty pictures, which would be a different filter wheel. This is for two spectrums, and then the blue and the V-type filter. So this is that CCD camera now. The CCD camera is monochrome, so we don't get the pretty color pictures that we were seeing before. This is, again, the object that we see directly through. And now the mount, this is on a mount, a telescope, and it's tracking. So this is a TeleVue NP127 IS, and there's a 5-inch refractor. And one of the first things you learned is something's in focus, everything else is out. So right here, where the spectrum energy, which is about right here where it gets real narrow, that's the focus point. And we can see H beta, we see gamma, delta, epsilon, zeta, and literally we can see all the bomber even out here. If I change the focus, notice how this changes a lot. And now what's happened is I see a lot better detail up here where H alpha is. These are O2 and oxygen absorption lines in the atmosphere. But notice, I'm losing detail down here. So back up. I don't see any detail here where the H alpha is. I see plenty down here in the short wavelengths. Oops. Here, I'm seeing better stuff up here with H alpha, but I start to lose that. So that's a trade-off with these types of filters. And one of the reasons is that the focal plane is curved. So the CCD is flat, and as a result, something's going to be in focus, and the rest of the stuff will be out. But it's good enough to get basically a sense of what we're looking at. So here's Vega. A, remember A is where the hydrogen Balmer series has strong. So here's a good balance between the H alpha, beta, gamma, delta, epsilon, zeta, and even eta down there. So that's an unusual ability to get the focus in the sweet spot that we could see all these. And then these are the atmospheric absorptions. By the way, how would you tell the difference between an atmospheric absorption and the absorption in the sun? Well, you just stop your pictures with the, start with Vega. Start your pictures with Vega directly overhead. And as Vega starts to go down and starts to set, it goes through more of the Earth's atmosphere. So these lines here change with the altitude of the star we're taking a picture. The ones that come from the star will not change, and those will stay fixed in depth. So the ones that change is how we separate and determine which are from our atmosphere contributing to the absorption lines versus the ones come from the star, like Vega here. So this gets very cool. When we deal with titanium oxide, we're dealing with modules. Instead of getting a nice neat line, we get bands. And that's because when the module has 2 atoms or more, it vibrates, it rotates, and it produces basically a band of spectrum lines that can absorb or emit. In this case, they're absorbing. So this is Betelgeuse, and it shows this what we call broad absorption areas caused by the molecule. Now let's talk about emission. So we got something radiating energy, hits this cool gas, and what happens is it radiates out and we see emission lines. Remember, if our telescope was sitting down over here, we would see absorption lines. But if we're looking not at the star directly, but it's at the cool gas and it's re-radiating in all directions, we see the emission lines. So, Wolf-Rayet stars, they come in carbon or nitrogen, and what they have is a disk of material around the star, and when the star's energy is hitting that disk, that cool gas is re-radiating out, and what you're seeing is like, here's carbon, and the 3 I's means that it's double ionized, and that's at 4650 angstroms. Here is triple ionized carbon, here's some H alpha, so literally we get a much different spectrum than what we've seen before. So in other words, in this case, we have some material, be it a cloud gas forming in a planetary system or whatever, and that's radiating, and we see basically the chemicals signatures as emission lines in that. Here we have is the ring nebula. So this is the zero order sitting here. The spectrum is smeared out, but notice it's very different. Instead of having there's a cursor here, but underneath the cursor we see a little bit of differences in the light. Here, we see, a duplicate copy and a duplicate copy. Well, this duplicate copy is primarily from the oxygen double ionized. In fact, this is called forbidden. And the reason it's forbidden is that we cannot really generate it in labs because we don't have the capability to do these very low densities. Also, H beta is also buried in here. So there's 2 lines of oxygen and 1 line of H beta, and it makes it very strong. Here's the H alpha. So, for those who are doing visual, if you have a filter that just takes a look at this portion of the spectrum, you're not, all this stuff outside, like light pollution, basically is not going to be affecting your observing. So literally, this explains why certain filters, if they line up on these peaks here, most of the energy of the object comes through, and we decrease the amount of light energy that we see at other wavelengths, and as a result, we have better contrast of what we see. In this case, it's literally a duplication of the object. Since these spectrum lines here are sufficiently far away from here, these are separated. As we were to, let's say, decrease the resolution of our spectrograph, these will eventually merge into a big mess as they come together. M101, ionized hydrogen. That area there, you say, well, okay, is that a set of stars, or is it something interesting like a gas? And what you can do is, you take that same orientations upside down, and you realize you end up with 2 lumps, just like we saw with the ring nebula. Those 2 lumps, basically, is a set of elements, and there's not a continuum. So that little bright thing, or that thing there, is not a star. It's basically an ionized gas of H, basically ionized first level of hydrogen. We go ahead and plot it out. What we have is 3 lines sitting in here, H beta. This is double ionized oxygen. And we've got 2 sets of lines, and we have H alpha sitting here. Now, next step with astrophysics is, depending upon the ratio of intensity of these lines, one can determine the temperature of that gas. So that's astrophysics to the next step. Okay, back here, this wasn't my intent of the picture. This was the intent up here. This lumpy little fat worm up here. That lumpy fat worm is not in the Solar Digital Sky Survey over here, but it's plainly here, and it's very bright. This was our supernova that occurred here in late summer and through the fall. And we're talking now outside our galaxy, so we're taking spectrums of things that are 16 million light years in the galaxy. And by the way, here's that H alpha, that ionized alpha hydrogen area. Here's another one, and each one of these has the same characteristics of that little spectrum I showed you before as distinct emission lines. So, key thing is this star blew up 16 million years ago, finally light captured here, came in, hits the telescope on the driveway here, and we record those photons as a set of light images, and we got this basically looks like a camel humpback. So we said, wow, is that absorption or is that emission? Well, what's happening is that silicon ionized to the first level, and these are broad bands because this normally is not at 6150, it's normally at 62, but because the speed of the material of the explosion, we now have a blue shift towards us, and a blue shift means that the features of the absorption band is gone to the left here because the short wavelengths is blue, long wavelengths are red. So, two key things. Other types of supernova, I see clear, basically, hydrogen lines. They're not here. This key thing of the silicon ionized to the first level is only occurs in supernovas of a 1A type class, and this is the hallmark of knowing that it's a supernova 1A. Now the key is that this small white dwarf accumulated enough mass that when it was at 1.4 masses of our sun, because of the laws of physics, it blows up. And because of that, we know its brightness. Because all of these things that blow up at 1.4 times the mass of the sun have basically the same amount of luminosity. So we can use these as a distance indicator to see how far that's away, because we know how basically bright it should be. And depending upon the photometry measurements of how dim it is, we can then basically adjust and say, its absolute brightness should be here, but because it's this dim, it must be so far away. So literally these are excellent standard candles in order to determine things that are very far away as to what their intrinsic distance is, because we know they blow up and they're certain brightness. But the key is that there's lots of different supernovas. And this happens to be one of the more important ones that has this characteristics of being known brightness when it blows up, because it blows up at 1.4 of the sun's mass. So, we talked a little bit about blue shift, red shift. So, here we have an observer here from our driveway. And as the object in this case is moving away like that, the wavelengths get stretched out. Now the little graph shows that if the object's moving towards us, in other words, if I take the observer and put it over here, notice that the wavelength peaks are compressed. This is very similar to a siren or a train that goes by you and you hear the shift of the frequency as it goes from something very high to when it leaves you, basically low. So if you're measuring the spectrum features and you know what it is at rest, in other words, it's not moving respective to you either away or back, we have a set of absorption lines here. If it's redshift, the wavelengths get all longer. Hence, this line goes towards the red. This goes already in red, even more red. If the object is coming towards us, like up here, fundamentally, the wavelengths get compressed. That means shorter wavelengths is shorter, in other words, the blue end of the spectrum. So this is how we use measuring the spectrum indicators, or in other words, the absorption lines or the emission lines. We can determine whether or not the object's moving towards us, or away from us, or standing still. So this was the whole objective of my getting into spectroscopy, is measuring this little white dot. That's typical of quasar. But notice that its spectrum is lumpy. Notice that all these other spectrums look fairly the same. In other words, they all have some atmospheric effect. What's common to all of them is they have some atmospheric notches at the tail end up here in the red area. And again, they're not colored because this is a monochrome camera. So, right here, we take a look at that, and we're going to take a look at that little smear of light there. That smear of light here basically zoomed in. There's our 3C273. Martin Schmidt at the 200-inch Mount Palomar telescope in 1962, excuse me, the fall of 61, took a spectrum of it, and it baffled him. Then the aha came to him. He published in Nature article in March of 1962. He said, these things here are part of the Balmer series, hydrogen. But they're not where they're supposed to be. So H alpha, which is normally 65, 63 over here, is way over here. So H alpha 65, 63 suddenly was a difference of 1,039 angstroms longer, hence redshift. And it comes in at 7602. And sure enough, if you take a look at the O3 and H beta and even the H gamma, you find that if you use a redshift calculation of 0.158, they all appear correct in the graph, basically, of this spectrum. And that means that literally this object's moving away from us, and it's moving away at a 0.158. Now, just as a side note, 7,000 angstroms is where we usually stop seeing. This is the deep red. Here's the real short wavelengths in blue. This is ultraviolet. Notice that the hydrogen alpha, we would never see that in an eyepiece. It's beyond our, basically, the frequency is too low. We're getting into the infrared area here. But the nice thing with electronic cameras is they do have sensitivity into the infrared. And that provides us something that Martin Schmidt didn't have. When Martin Schmidt did this, he was using film. Film is very sensitive in the blue, but it's not very sensitive up in here. So he did all his calculations and publications on these lines. It wasn't until 2 years later that he got a hold of the electronic detector, and they confirmed that the H alpha was truly matched in here, and that sealed the case that his paper was correct and that this was a redshift of 0.158 for 3C273. So, other quasars. So this is the one of interest. Ryan in the audience, he was with me 2 summers ago, and we were at Old Asmuth Workshop at Pine Mountain. This was with a 6-inch Mac, and we took a picture of this. And some of the things you got to be careful. You got to rotate the camera just right so that that star's not in the spectrum. So one of the things you got to do is make sure that you have a clear path. Notice that this little dot below that, there's a little star below this real bright one, that stops basically the analysis of that spectrum. The other thing that was really neat was unexpected bonus. I mean, these are typical stars with their atmospheric absorption here at the tail end. But look at that star. Wow, look at that. To me, it was more interesting visually than this one. I mean, look at all those lumps. And not only that, the distance from here to where it starts is considerably longer than the distance here or the distance here. This is an infrared star. In other words, almost all its light starts in the red and goes up to the infrared. That's where all the energy, all this stuff here is because the camera can analyze the infrared. So getting back to our prime candidate. So we do take a picture of the spectrum and we do the analysis and smear it out. And gee, it looks very similar to 3C273, except it's shifted much greater. Notice that 76 was where H alpha is. Notice that this is now at 8,500. And I found that amazing because I didn't know that my camera was capable of going up that high in the infrared. Notice that the H3 peak, in other words, is separated from the H beta. In fact, literally, this is where normally H alpha is in 6,500 angstroms. And then here's H gamma. So this has a redshift of almost twice. In other words, 0.296. To put it in time perspective, 2 summers ago when we collected that light left that quasar through 8.2 giga light years has been traveling. And those little photons hit a piece of glass that smeared out And fundamentally, the self-aware universe that we are able to recognize what we were seeing as a distant object and not just a typical star in our galaxy, but something way beyond it. And give you a perspective, our solar system started about 4.5 giga years ago. So this is almost like 3/4 of our age of our solar system when that light started. Okay, next steps. This is a spectrograph that uses a grating. Again, a lens up here, a flip mirror to see where I'm aiming at, a slit in here to basically do creates a very fine slit to go through here. Another flip mirror to take a look at the back of the slit to make sure I got the star in the slit. So if you think of pointing a telescope and putting something, trying to put a star on something that's only 25 microns wide becomes a real challenge in keeping it there. And then of course it goes through another lens up here, hits the grating and comes back in. So this is my current generation. I threw this on a tripod, took a picture of Vega, and again, just let the star drift down through the slit of Vega, and we can see the H alpha here, the H beta, here's H gamma, and basically we got epsilon and delta sitting here. So a lot more stuff that can be done here, and that's in the future. Now, I have a website. You can basically, if you go to the spectroscopy link index, this is a list of the links in my index. I have this presentation in PDF, you can download it. So if you want all those little URLs and stuff on the bottom of the screen, you'll be able to download the PDF. And again, my website is stargazing.net/David. And you just go scroll down, and on the bottom of this webpage, you'll see a nice spectrum of Vega. Click on that, and then you'll see basically the presentation. Okay, can we have the lights on?